Welcome. Let's begin our journey into the fascinating world of salts, not just what they are, but how they behave. Have you ever wondered why some salts are colorless, others brightly colored, or why some dissolve easily while others don't? The answer lies in their physical and chemical properties, which shape their behavior in nature, laboratories, and industry. From crystal structure to acid base reactions, understanding these properties is key to identifying salts and predicting their uses and reactions in real world applications. Ever noticed how some salts form sparkling crystals while others show vibrant colors? That's their physical identity speaking. Most salts are crystalline solids with regular geometric shapes. They have high melting and boiling points due to strong ionic bonds. While many are colorless, salts with transition metals often exhibit vivid colors, like blue copper sulfate or orange potassium dichromate. Some salts are hygroscopic, meaning they can absorb moisture from the air. A notable example is calcium chloride. Can a salt dissolve in water or absorb moisture from the air? That depends on its solubility and hygroscopic nature. Solubility is a key characteristic. Nitrates and most chlorides dissolve easily, while carbonates and sulfides are often insoluble. Hygroscopic salts absorb water vapor, while deliquescent salts go further, they dissolve in the moisture they absorb. Calcium chloride is deliquescent, and anhydrous copper sulfate turns blue when it absorbs water, revealing its hygroscopic nature. What happens when salts are heated? They decompose, often with dramatic results. Many salts undergo thermal decomposition, releasing gases and forming new solids. For example, sodium hydrogen carbonate breaks down into sodium carbonate, carbon dioxide, and water vapor. Metal nitrates, such as lead nitrate, decompose to produce nitrogen dioxide gas and oxygen, often seen as brown fumes in the lab. Salts may look stable, but in the right conditions, they can react, releasing gases or forming solids in seconds. Acids react with salts like carbonates, releasing carbon dioxide gas, a key test in identification. Strong bases can displace weaker bases from salts, for example, sodium carbonate reacting with calcium hydroxide to form calcium carbonate and sodium hydroxide. Double decomposition between two soluble salts can form a precipitate, an important step in salt analysis and synthesis. From baking powder to batteries, the uses of salts depend on understanding their unique properties. Colorful salts are used in pigments and dyes, while soluble salts are key to water softening and chemical extraction. Thermally unstable salts, like sodium bicarbonate, are used in baking powders for gas release. Hygroscopic salts serve as drying agents in labs and industrial setups. By knowing a salt's properties, chemists can choose the right salt for the right job, making chemistry both efficient and practical. Let's wrap up with a quick recap of salt properties and their importance. The behavior of salts depends on factors like ionic composition, bond strength, and solubility, all of which influence how they react and where they are used. Most salts are crystalline solids with high melting points, and many, especially those of transition metals, show distinctive colors. Chemically, salts undergo thermal decomposition, neutralization, and precipitation reactions, which make them incredibly versatile. Properties like hygroscopicity and solubility are harnessed in lab drying agents, water treatment, and chemical separation methods. Understanding these properties helps chemists identify salts, predict chemical behavior, and apply them effectively in both science and industry.